Hello everyone. Well, if you are year 13 student doing OCR chemistry, then after about 13 or 14 lessons that I have recorded so far, this would be the one, the start of organic chemistry module 6, the start of your year 13 stuff. Remember, when I go through the year 13 topics, it is expected that you guys know all your year 12 stuff, particularly module 4, if I'm talking about module 6, which is also organic chemistry, the next level up. Right, let's see. Electrophilic substitution, module 6.1. Let's start very quickly that the whole thing, aromatic organic chemistry, it's got its root in this molecule, or rather the presence of this molecule, which is known as benzene. When this molecule was accidentally discovered or proposed by Kekulé, he actually proposed that the formula C6H6 has this structure, 3 double bonds and 3 single bonds. When as chemists we became cleverer, we were able to analyze things a little bit better, we realized that there are no double bonds in benzene. Because when we add, for example, bromine to this, it does not decolorize. Or the bond lengths or the bond enthalpies do not correlate to either double bonds or single bonds. Or the enthalpy of hydrogenation, when, for example, double bonds here, as proposed by Kekulé, react and get saturated with hydrogen, the enthalpy of hydrogenation is not the same as, for example, when alkenes react with hydrogens. The enthalpies are different. So it kind of puzzled people. And ultimately, we realized that Kekulé's structure between you and I isn't exactly correct. What is correct is that these bonds, or rather the pi bonds, because you know each double bond comprises of a pi and a sigma. The pi's actually side overlap with one another, all of them with one another. If I may draw a very quick benzene molecule, say sideways. Now, this is where I actually go a little bit overboard with my own students here, and I talk about sp2 hybridization, which is not even in your syllabus. In fact, it's due to the sp2 hybridization that you can understand where carbon-carbon double bond comes from. But you will probably learn that more at university. But each of these carbons have a p orbital that were not involved in this hybridization. So what happens ultimately, I mean, if Kekulé's suggestion was that these two side overlap, forming a double bond there, but these two don't. These two do, but these two don't, and these two do. So you have 3 double bonds and 3 single bonds, whereas that is not the case. What is the case is that all of these p orbitals above and below, right, and below the plane of the benzene molecule side overlap with one another. And as a consequence, in a very simplified version, we just use a circle, where the circle is the area of delocalized pi electrons between you and me. There are 3 pi bonds, which is 6 electrons, and these guys don't have any locality, and therefore they're referred to as delocalized electrons. An area of where electrons are. Now, what kind of chemistry is benzene molecule involved with? Well, it is involved with species that want electrons, and therefore they should be having perhaps a positive charge, i.e. they are going to be electrophiles, isn't it? In these electrophilic substitutions, Most of your job is to find out or to learn how you actually generate these electrophiles. If you do that, you've done 50-60% of the job. We always start with this example, nitration of benzene. Let me write the formula. You can either write C6H6 or you can just draw the structure, skeletal formula. Sometimes this might be even faster. You need nitric acid, which is concentrated, and then you need sulfuric acid, which is also concentrated, but this one is used as a catalyst. And then what you produce nitrobenzene plus water. That is the equation. Well, I mean, that will land you 1 mark. You know, A-level students, they will ask you, how did that happen? Let's break this thing up. What is the role of sulfuric acid here? Nitric acid, which is a very strong acid, sits next to sulfuric acid, both of them concentrated. But sulfuric acid is a stronger acid. Sulfuric acid is going to act as an acid, forcing nitric acid to act as a base, a proton acceptor. You can imagine if you were nitric acid, you wouldn't like it, would you? So your HNO3 becomes H2NO3 plus, with a plus charge, plus sulfuric acid that has lost one of its protons, and therefore it's HSO4 minus. Now you might be thinking, I said sulfuric acid is a catalyst. How is it that it is being consumed? We will see later on how it is regenerated. But what about this guy? Doesn't like the situation one bit, does it? It is highly, highly unstable. And what does it turn to? It immediately turns into water and a nitronium ion. Didn't I tell you something with a plus charge? There we have it. Nitronium ion. So now the crucial point. Like I say, you can always go back and watch this again. So if I change pages quickly, don't panic. You've got the video. So, reaction mechanism. The NO2 plus is now in the pot. And we are heating this under reflux condition around about 50-55 degrees Celsius. Remember, nitrobenzenes, or they could potentially be explosive materials. I mean, TNT is trinitrotoluene. It's like you get toluene, which is methylbenzene, and then you trinitrate it. It's TNT. So you have to moderately heat these things. So what happens now? Remember, I told you electrons come from where electrons are, and electrons are exactly there. You have to take your arrow from where the electrons are, and imagine telling this NO2 plus, hey, come and make a bond with me. Now, that arrow is a pair of electrons. A bond that is going to form a bond with NO2 is a pair of electrons. 6 electrons in there, losing a pair of electrons. So how do we actually write the intermediate stage? So now that NO2 is there, and now we show the hydrogens that in a skeletal formula we don't show, right? Because it's this that is going to substitute that. So you have to show what is happening. But what about the ring? Well, the ring has lost 2 electrons. How do we show that on a piece of paper? Well, you have to draw a semicircle with respect to that being number 1, from the 2nd position to the 6th position. Don't go beyond, you lose a mark. It's lost a pair of electrons. Okay, put a plus charge there to show it's lost a pair of electrons. So what's the next step? The next step is hydrogen gives up. Say, hey, you can have my electrons. I am off as H plus. And then you can have the intended product like you wanted. Nitrobenzene plus H plus. H plus. What happens to that one? Oh, remember your H SO4 minus, it gains that H plus and regenerates sulfuric acid, your catalyst. So when you add 5 ml of sulfuric acid in there, it's always 5 ml in there. Now you may argue, but that hydrogen isn't the same hydrogen it had before. Who cares? It's hydrogen, isn't it? And therefore your sulfuric acid is always retrieved. The other thing I want to tell you in brackets is that reaction mechanisms are proposed by chemists. Nobody sees these things going up and down, hydrogen being lost and positive charge being formed, intermediate stage, this, that, and the other. They come up with some rational ideas as to how reaction mechanisms takes place. And if it is agreed by a bunch of very clever chemists, then they'll accept that. Yeah? But like our good friend Kekule, if in 10 years, 20 years time, people find out that all these things we've been talking about is absolute nonsense, then of course they can propose something slightly better. But for the time being, this is what it is. All right? If I may include maybe just a couple more examples. So if you want to do halogenation of arenes, let's say for example reacted with chlorine, you have to use what is known as a Friedel-Crafts catalyst, also known as anhydrous aluminium chloride. So what happens with aluminium chloride? It actually reacts with chlorine and it produces aluminium tetrachloride plus something you've never seen before. Chlorine with a plus charge. And then the reaction mechanism, exactly the same as nitration. So you have that attacking, in this case, chlorine, and then it produces Cl, H. Do you see the similarity? Plus, and then hydrogen comes here, and then you produce chlorobenzene. Plus H plus, and then H plus goes and reacts with aluminium tetrachloride. Your aluminium chloride is retrieved, catalyst, remember, plus HCl. So if you do this reaction under basic conditions, for example, based on Le Chatter's principle, HCl is removed and the reaction goes forward much faster. Because when you remove HCl from the right-hand side, the reaction is pursued. But you see the similarity in reaction mechanism? What about alkylation? What about if you want to produce methylbenzene? You react it with a corresponding haloalkane, chlorine, and you can use Friedel-Crafts again, right? And then if you use Friedel-Crafts plus CH3Cl, you can then produce AlCl4 minus plus CH3 plus. And then the reaction mechanism is exactly the same as you've already seen the other two examples. So you end up making methylbenzene. Right? And then if you, methylbenzene, when I was doing chemistry at degree level, this thing used to be called toluene. Now, it's got a generic name, toluene. So if you nitrate it 3 times with nitric acid, you get nitro there, nitro here, and nitro there, trinitro, toluene, TNT. So, to wrap it up very, very quickly, it's in chemistry, it's not important as to what is it that you have, is what is it that you can do with it. And later on in the course, you might be asking, so what is the purpose of making nitrobenzene? Well, we can turn that into something slightly more useful, but that's for another day. All right? As we can turn methylbenzene into something else. That's another day. At the back end of your module 6 is organic synthesis, which talks about, in essence, how we can convert one functional group into another functional group. But more or less that wraps up electrophilic substitutions in aromatic organic chemistry and catalyst reaction mechanisms, balanced equations. You need to know them all. Okay? It's not a matter of if these things come in the exams. They will. You learn it, you add a few more marks to your paper. You don't, take a few marks off. That's how you have to approach chemistry A level. Thank you very much.